Well, hello there, Calculus 3 class. I hope everyone's okay and doing well. This is Mr. King, of course, and I would like to present to you the section 13.3, and it's over differentiation of multivariable functions. And so I think you'll find it fairly simple. It's a computational section, just really straightforward differentiation, except with respect to one variable at a time, not both variables. Yeah. So here we go. So I'll take you to our WebAssign homework page, and we will begin. Okay. So I hope this can help you, and let's do some mathematics, class. Okay. Here we go. Okay, Calculus 3 class, so here we go. This is section 13.3, as I mentioned. And yeah, so what we have here is this. We just finished the section on limits of multivariable functions, mostly concentrating on two variable functions. And now, and continuity and taking limits, and now we're able to then look at the partial, they call it partial derivative of a two variable equation, which is a surface. And I would like to first just show you a picture from your textbook. And so let's see here. So here is the equation of a surface here, and f of xy, so it's a function of x and y. You could also rename this the third dimension that's missing here, which is z. So every xy coordinate point and the xy plane, of course, which is down here, will have a mapping unless there's any restrictions, any divisions of 0 or square roots or anything, but there's nothing here of that nature. So the entire xy coordinate plane, every single xy point in the xy coordinate plane will have a mapping, will have a z mapping by substituting that xy coordinate point value, for example 1/2 for x and 1 for y, and if you plug that 1/2 for x and the 1 for y, compute, then you should get a mapping or range value, f of xy value or z value, all different ways of saying the same thing, equal to 2. And here is that point on the surface. And straight down would be the xy coordinate point, 1/2, and then out 1, so roughly in here somewhere, and then you go straight up to the surface, and there we are. And you can see they cut through with the vertical plane at y equals 1. And right here is where, and then they also drew a trace, a curve, which is a trace here at y equals 1 that comes down on this trace is the intersection of this plane and the surface. And so you get this curve, and they wanted to show you that curve so that at this particular point, we could have done this with any point, they had just had to pick one. And so we can differentiate this two variable function, and if we want to know what is the slope, this is the x-axis here, the y-axis, this is the positive x-axis, the positive y-axis, backwards would be the negative x-axis, of course, negative y-axis. So if we want to know what is, I'll write along here to see this this plane right here is parallel to the x-axis at y equals 1. And this plane cut through the surface, and it forms the intersection with that plane and the surface is this curve right here. It's not showing all of it. Well, this keeps going down forever, but it's showing enough. And if you would like to know, if we would like to know the slope at this point on the surface in the direction of, in a direction meaning this curve is not on the x-axis, but it's parallel to the x-axis, meaning this plane right here, y equals 1, is parallel to the plane y equals 0, which would include the x-axis here. So if you take a point on the surface and draw a tangent line, there's all kinds of tangent lines here on the surface, but the tangent line to this point on the surface, that is in the direction of the, see, it's in the direction of the x-axis. So it's not aligned right down here on the xy coordinate plane. That would be parallel to the x-axis. But it's in the same direction. And you can see this surface is going downward. It's decreasing. And it looks like it becomes even more a steeper decrease as you go this way. So the slopes would get larger and larger in a negative sense as we come along the surface. And so to find that slope value, which they've done, it ends up being -1/2. So the slope of this tangent line at this point, 1/2, 1, with surface mapping value 2, the slope of this tangent line is the same as the slope at this point on the surface, and it turns out to be -1/2. In a moment we'll show you, which is really quite simple, the computation part, how to compute the partial derivative of this surface equation with respect to x, which would then give us a formula so that when you plug the x and y value in, it'll give us the slope of that point on the surface in the direction of the x-axis. Over here you see the same point, the same surface, the same point, and then you see a different plane cutting through the surface. It's coming straight down perpendicular to the xy coordinate plane, or parallel to the z-axis, and it's cutting through at x equal to 1/2. If you come out just 1/2, that's 1 unit, 2, 3, 1/2. The plane of x equals 1/2, and that plane cuts through and it intersects the surface, and it gives you this intersecting trace curve, which is similar to this, but it's this way. And so by the way, this is some kind of elliptic paraboloid that it's facing downward and shifted up this many units, 25/8, which is a little more than 3 1/8. There's 3, there's 4, 3 1/8. And now, if you would like to know the slope of this surface, again, at the same point as this one. You're like, wait a minute, we already did it and we got negative 1/2. Yeah, but that was, because this is three-dimensional, we can now find the slope on this surface coming from different directions. And in this section, we're going to only talk about in the direction of the x-axis, which is this one, the x-axis. You intersect the surface with a plane at, the plane is a vertical plane, and when it cuts through, you get this curve, and then the slope at this point on the surface in the direction of the x-axis is the slope of this tangent line in the direction of the x-axis, and when that's the negative 1/2. And here, it's in the direction of the way the y-axis moves. And by the way, you might think, well, isn't it going upward? Shouldn't it be a positive slope? Well, you have to move from, just like we did with single variable functions, you had to move from left to right as you looked at a function to say if it's increasing or decreasing. You had to move from left to right. Another way to say left to right is from negative values to positive values, the negative x values to the positive x values. The same thing here. You have to move from negative x values to positive x values in that direction, but we're just moved over here at y equals 1, because that's the point where they want us to find the slope on the surface at y equals 1 in the direction of the x-axis. And so as you move from the negative x values to the positive in this direction, the curve is coming down, and right here the tangent line is a negative slope. Same thing on this one with respect to the y direction. Here are the negative y values, and so you're coming along, and the surface is incomplete here, but as you move in closer to this point on the surface, and now you're coming up over the top, and now you're coming down, and right at this point, this point right here is on the surface, and it's also on this plane that cuts right through the surface, and this plane is at x value equal to 1/2, as I said it. And so where that plane intersects that curve, you don't have to have the plane drawn there, it just helps us see the trace, which helps you see the nature of the decreasing nature of the surface right at this point in the direction of the y-axis. In the y direction, I should say. And again, that's going downward, decreasing, and it is steeper, more in a downward fashion than this one was. And so that's why the slope is a bigger number. It's -2 versus -1/2. Well, I hope that makes sense. All we have to do now, which is the easy part, is talk about how to differentiate a function of two variables with respect to the x direction or with respect to the y direction. And because we're only taking the derivative with respect to the y direction only or the x direction only, then we don't call it a complete derivative. It's called a partial derivative. And that's all we can do with two variable functions. So when you differentiate, for example, with respect to x, there's all kinds of notations for it. And I'll show you some as we go along. Well, several. Here's one notation. If the function's called f of x, and it's a function of two variables, x and y, then the partial derivative of f with respect to x and y separately, with respect to x only, is this notation. The derivative of f, which is a two-variable function, and what are the two variables, x comma y? What are we going to differentiate partially with respect to x? And here is the same notation. The partial derivative of this two variable function x comma y with respect to the y direction. Now, how do you get these partial derivatives? Very simply. When we learn to differentiate class, if there's a constant term by itself, we know the derivative of a constant by itself with respect to any variable, with respect to x or with respect to theta or with respect to w, whatever, it's 0. And when we have if you have for example, this is a negative 1/2, if you're differentiating this term right here with respect to x, this negative 1/2 is a multiplied constant, multiplied negative 1/2, and it's not sitting by itself by addition or subtraction, because if it was, it would be like this, and the derivative would be 0. But when it's a multiplied constant in front of a variable, well then that multiplied constant sits there and waits for you to differentiate the variable, and then when you differentiate it, whatever you get, it's times that constant, that multiplied constant, negative 1/2, that was waiting. Now, if we differentiate this two variable function with respect to the x direction, then the y variable is frozen, considered to be a constant, just like the 25/8. And in this case, this is the only place where there's a y variable in this two variable function, f of x comma y. And so because it's all by itself, it's not times right here next to the x squared or something. So because it's by itself, then when you differentiate partially with respect to x, then the other variable is considered, you treat it as a frozen value of y, like a constant. And then the derivative of that constant by itself will be 0, just like the derivative of this constant will be 0. Therefore, the partial derivative with respect to the x direction of this one will be this derivative, the derivative of this term will go to 0, the derivative of this term will go to 0. This is the only term that has an x in it, so you differentiate this with respect to x. So use the power rule, bring down the 2, and negative 1 times the 2 you bring down, divided by this 2, will be negative 1. X to the 1 will decrease the exponent by 1, so the 2 decreases by 1 unit, and you get x to the first power. So you bring down the 2 times the negative 1/2, which is already there, and that becomes a negative 1 x to the first power. Negative 1 x to the first power. Or you just say negative x. So that is the partial derivative with respect to the x direction. And therefore the slope at this point, at the domain value point, which was the 1/2 comma 1, whose mapping comes up to this point on the surface, but when you plug in the point to get the slope, you only plug in the x and the y variable. And when you plug in 1/2 for x and 1 for y, well, there's no place to plug the y value right here, so you don't substitute the 1. This y equals 1 doesn't have an impact on this particular derivative right here, but the x does. So you put the 1/2 in for x and you get negative 1/2, and there you go, which was the slope of this right here. To differentiate with respect to y, in the direction of y, I should say, and you can say with respect to x or with respect to y. So now look at this equation again. The 25/8 is a constant, and the derivative of a constant is 0. The derivative of negative y squared, it's all by itself, and the derivative with respect to y, now you use the power rule, bring down the 2, and it'll be negative 2y. This term doesn't have any y's in it, So it only has x, so you treat that as a constant. My cat's going berserk over here, running all over the place. Anyway, so if you hear some noises, that's the cat. So the derivative of this will be 0 because this is treated as a constant. And so this will be 0, the derivative of this will be 0, and the derivative of this, you just bring down the 2, it'll be negative 2y to the first power, right here. Now, if you want to know the slope at this point in the y direction, then you plug in the 1/2 comma 1, because that's all this is a function of with respect to x and y. The third variable, z, is the mapping value, the range value. My cat is really having fun here. So, what here, you only plug in the y value. So the x value has no impact right here on this. That doesn't always happen, by the way. And so you plug in the y value and you get negative 2 times 1, which was the negative 2 that it showed us down here, which was the slope right here. Well, I hope that makes sense. Okay, so now number 19, they give us a function, a two-variable function with respect to x and y, and then they put it in context of something, and they're saying that there's a steel plate. They don't tell us where this steel plate is, and has it just been removed? Is it in a furnace? Is it they pulled it out of a furnace? Who knows? They don't tell us. And then they place the origin somewhere on the steel plate. They put the and so depending on where you are on the steel plate, the temperature is what's changing everywhere. So, but in certain places it's changing faster or slower. The rate of change of the temperature with respect to the distance from the origin will be different. And so they're asking at a particular point on the, so this is a point on the xy coordinate plane that will have a mapping by plugging the 10 right here and the 2 right here, and then compute, you'll get the range value, in this case the t value, and I'm losing my concentration. Sorry, with the cat. Never seen her do this much. Anyway, I think she gets all happy when she hears me talking mathematics. And just kidding. I'm not a cat crazy person, okay? Anyway, so all we're going to do then is find the partial derivative in the direction of the x-axis and the y-axis, just like I showed you in the textbook. So then it just boils down to take the derivative of this two-variable function partially with respect to x, and then that'll be one formula. And that'll be the slope formula, or the partial derivative formula for the slope along the surface at any point in the direction of the x-axis. And likewise, we'll take the derivative of this partially with respect to y, and that'll give us the derivative formula for the slope on the surface at any point in the direction of the y-axis. In the y direction, because it can be kind of misleading if you say the y-axis. In the same direction as the y-axis. Okay, so let's do that. So here is the equation. I put in the GeoGebra and I put in a equation, but I didn't put in 800. I just put 8 because I was having trouble getting it to show nicely if you make this go all the way up to 800. So this is similar though. And this goes downward forever. And because I don't have the exact 800, then the point 10 comma 2, that would be like right here, but it's not in the right place. But we can just imagine that like it's a point like right here or right here. And now we're going to find the slope in the direction of the x-axis and also in the direction of the y-axis. And it looks kind of like similar to the one I showed you in the textbook. So you'd expect in the direction of the x-axis, this is coming downward. So you could see if you cut through here with a plane, a vertical plane, it would make a trace, and then that trace at that point, the tangent line would be in the direction of the x-axis. It would be, this is the x-axis, so it would be something like this, and you can expect that's going to be a negative slope. In the direction of the y-axis, and you got to make sure we're going from negative to positive. This was from negative to positive. From negative to positive y direction, now you're coming this way. And so as you come this way, you cut through with the plane now. And when you cut through, you're going to get a trace, this kind of trace. And then the slope at that point in the direction of in the y direction, it'll be a tangent line, something like this. Kind of hard to get it exactly, but it's going to also have, it's decreasing here as well, and you'll have a negative slope. So let's take the partial derivative with respect to x. And as I told you, there's different notations for it. Here's one notation. It's probably the easiest. If the name of the function is t, capital T, then the partial derivative with respect to x is just, you just put this in a subscript, the x. And that means the partial derivative of t with respect to x of this two-variable function. Here's another notation for the partial derivative of t with respect to x. Instead of a d and a d like the first derivative, they're using this Greek variable here. And so that's another notation for the partial derivative. To differentiate this with respect to, partially with respect to x, then again, here's a term, here's a term, here's a term. When you differentiate partially with respect to x, the y is considered a constant, a fixed constant, just like 800 is a fixed constant. And the derivative of this constant all by itself is 0. And so, even though I know there's a negative 1.2 times a fixed constant value y squared will still, altogether, this would all compute to some number. So then the derivative of this will be 0. And now you just differentiate this term with the power rule with respect to x, bring down the power. Negative 0.5 times 2 would be negative 1, x to the 1 less power, so x to the first. So it would be negative 1x, or negative 1.0 x, right there. Now plug to get the slope in the x direction, like I was showing you on that surface. You plug in the point x equals 10, y equals 2, because that's the coordinate point in the xy plane whose mapping goes up to the surface. And so to get the slope on the surface at the x value 10 and y value 2, you just plug into your partial derivative. Wherever there's an x, you put a 10. If there is an x, there is one. And if there's a y, you plug in a 2. There isn't one. Sometimes there will be, though. And now compute. So negative 1 times the x value 10, well, negative 1 times 10 is negative 10. And this, they told us in the problem, it's degrees per meter. So that means on this surface, which I don't quite have the right one, but it's bigger, because it goes all the way up to 800, it makes this quite a bit bigger. So in the direction of the x-axis, when you, right here at this point, that partial derivative slope value means if you were at this point right here only, if you were to go 1 meter out on that metal plate, the metal plate looks like this, by the way. Then as you would go out in the direction 1 meter in the x direction, the temperature would change by 10 degrees, decrease by 10 degrees. And they don't tell us if it's Fahrenheit or Celsius. It doesn't tell us. Now do the same thing with respect to y. So right here, the partial derivative of t with respect to y, or you can write it as t, capital T subscript y of the function, that's a two-variable function. Come up here to these terms again, differentiate partially with respect to y. So anywhere there's an x, you treat it like as if it were a constant. If this is a constant, pretend this was a 4 squared, well, that would be 16 times negative 0.5, which is a half. So that would be negative 8, and the derivative of negative 8 by itself would be 0. So this, and you say, well, how do you know x is 4? Well, I don't, but it can be any fixed constant. So regardless of what fixed x value it is, the derivative will still be 0. And the derivative of 800 by itself is 0. So now you differentiate this with respect to y. Well, now this is a variable, varying, and this is fixed. So this you differentiate and you bring down the 2, power rule, negative 1.2 times 2 is negative 2.4. Y to the 1 less power, so y to the first. So negative 2.4y. Now find the rate of change in the temperature on that point on the surface of that metal plate, but in the y direction now. The same location on the surface of the plate, pretend that was the point. But now if you're going in this direction, now this is big, right? This is big. So you think 1 meter, that's a long ways, but this is a big surface. And if you go 1 unit in the y direction, which in this case is 1 meter, the rate of change of that temperature would decrease by, well, whatever we get right now, which is the negative 2.4 times, put in the 0.10 comma 2. There is no x variable here to put a 10 in, but don't think that that's always going to happen, because it won't. You'll see in the next problem, actually. There is a y variable, though, still in this partial derivative with respect to y, and so you plug the 2 in. Negative 2.4 times 2 is the negative 4.8 degrees per meter. And so that's the rate of change at that surface point on the metal plate, but in the direction of, in the y direction. So anyway, so I hope that makes sense. So we got negative 10 and negative 4.8. And there you go. And we're good. Let's do number, well, let's do number 11 next. So here's a graph of a surface that's defined by this equation, this function's equation here. And they named it h of xy. They could have named it f of xy or g of xy. And all this is equal to, could be replaced by the mapping variable, the range variable, which would be the z-axis. So this all can be named z equals x squared minus y squared. And now they want us to find the slope in the x direction, the slope in the y direction again, just like on the previous problem, but it's a different surface. And the point this time is that x equals 3 and y equals 1. And if you put negative 3 right here, square it, and put 1 here and square it, you get 9 minus 1. And 9 minus 1 is 8. And so 8 is the range value, the mapping value, the function value, or the z value. And that's why they show you this z value, 8. And that's this point right here. So x is, and it's kind of hard to see, they didn't label these that well, but this is the x-axis and this is the well, I'm not sure, to be honest. Can't really see this very well, but maybe it must be, this is the negative 3, the x-axis, y is 1 this way, and then you go straight up. But I can't tell with absolute certainty. And it kind of looks like they got the y over here more, but I can't tell for sure. But here's the point. So I can't help that they didn't draw it that well for us to see. But anyway, so we're going to compute the partial derivatives, and then we'll plug in the x and the y value. So this is number 11. I just have to find it. So x squared minus y squared So here we go. Number 11, h of x comma y equals x squared minus y squared. I already told you about this. Note, at x value negative 3 and y 1, which is on the xy coordinate plane, you plug that into the two variable function, h of xy, and you get a mapping value, a range value, a function value, a z value, which is that 8. So z equals h of negative 3 comma 1, which is 8. And so another way to say that is this three-dimensional coordinate point, negative 3, 1, 8, is a point on the surface of h of xy. And then they're going to ask us, just like we've done on the previous problem, find the slope in the direction of the x direction and the y direction. So the slope in the x direction of h of xy at the point negative 3, 1, comma 8 is, well, first take the derivative. Well, I wrote it this way. Here's more notation. H, partial derivative of h with respect to x. This is saying that h is a two-variable function of x and y. At, find the slope where? At the point negative 3, comma 1, comma 8. But the derivative formula can only have x's or y's in it, not z's, because this is a two-variable function to begin with. So over here you only have x's and y's. So when you differentiate with respect partially to x or with respect to y partially, then you cannot have any z's over there. So the z equals 8 value would not go into the derivative. Only an x or a y value, or both. Well, the derivative of this with respect to x, so x is the variable and the y is a constant, fixed. And so you treat it like, just like if it was a number. If this was 5 squared, which would be 25, then the derivative of negative 25 by itself would be 0. If y was negative 2, negative 2 squared would be 4, and then it would be minus 4, and the derivative of negative 4 is 0. So regardless of what y is, when you fix it, hold it constant, the derivative of this will be 0. And the derivative of this will be, well, you got to use the power rule, bring down the 2x to the first power, 2x. And now plug in the point negative 3, 1. X is negative 3, y is 1, but there is no y value in the derivative formula yet. So you just plug the x in and you get 2 times negative 3 is the negative 6. The slope in the y direction, same idea, but now in the y direction, you have to take the partial derivative with respect to y. And so when you differentiate now this with respect to y, this variable x is considered a fixed value, some fixed value of x. So that's like, again, if it was like a 7 squared would be 49, and the derivative of 49 would be 0. So the derivative of this will just be 0. Now this is the variable this time. So then you differentiate it with respect to y. And so you bring down the power, negative 2y to the first power. Now plug in the point, negative 3 for x, y is 1, but there's no place to put the x in right here. So you only can put the y in, and negative 2 times 1 is negative 2. And so those are our two slope values at the same point on the surface, but just in different directions. So that's what happens when we have a surface. Now, there could be times when the slope's the same in both directions, but not in this case. So negative 6 and negative 2. So, hope that makes sense. Next, I'd like to help you with number 10 class. And here is the function, arctangent of y over x. So it's a two-variable function with respect to x and y, which is what it says here. They named it f. So this is a surface. And if you take the domain point, x is 8 and y is negative 8, that's a point on the xy coordinate plane which has a mapping. You plug that in here, by the way. For y, put the negative 8. For x, put the 8. Negative 8 divided by 8 is negative 1. Arctangent of negative 1 in radians, it's negative pi over 4. Negative pi over 4, if you put that in the calculator, it's somewhere around negative 0.8-ish, negative 0.8 around there. That would be the range value, the z value, the range mapping value of the function f. And now they want us to find the slope again at this point, which maps onto the surface. And now that point on the surface, what's the slope in the x direction and the y direction again? So the same idea as the other ones, just a different surface equation and a different point. So we're going to have to differentiate arctangent with respect to x and then differentiate it with respect to y. Okay, so let me show you that. So number 10, so here's the function, here's the point. Now the partial derivative with respect to x of f, which is a two-variable function with respect to x and y, there it is. Now how do you differentiate arctangent of inner expression? Well, the derivative of arctangent is 1 over, you could look on a formula sheet, it's 1 over 1 plus the function that's inside the arctangent, the expression that's inside the arctangent function. So 1 over 1 plus this inner expression, quantity squared, times the derivative of the inner expression, with respect to, in this case, with respect to x. So now we got to figure out what's the derivative of this with respect to x. So we now consider y a fixed constant. Pretend that was like a 4 over x, and you have to differentiate 4 over x with respect to x. Well, then you would just bring it up, bring the x up, and it becomes x to the negative 1 power. And you'd have like a 4 times x to the negative 1, and now you could differentiate it with the power rule. But instead of a 4, it's just a fixed, 4 is a fixed y value, but you leave it in general and just say y, knowing y is a fixed constant. And then times x to the negative 1, differentiated partially with respect to x. So you freeze y, and because it's not y plus or y minus x to the negative 1, so this y, just like if this was a 4, you would the multiplied constant would sit there and wait in the front for us to differentiate the x. So the y stays multiplied, bring down the numerical exponent value, power rule, to differentiate. So it'll be negative 1 times the y that's sitting there, times x to the 1 less power. What's negative 1 minus 1 more? It's negative 2. You can move this back underneath as x positive to the positive 2 power, or squared. And then the negative 1 times y is negative y, and that remains in the in the numerator. So here's the partial derivative. Oh, that's just the derivative of the inner function, this part. So now I did that on the side. Now we're going to move that over here. So what's the derivative of arctangent of this inner expression? 1 over 1 plus the inner expression quantity squared times the derivative of the inner expression with respect to x, which is this over here. So that's why we have the times negative y over x squared. This is the derivative, partial derivative of f with respect to x. We could probably just put this in WebAssign. Not sure, I didn't try. But I also just said I'll clean this up a little bit algebraically. This is y, well, I wrote it down. This is, so 1 times this fraction. There's more than one way to clean it up also, algebraically speaking. 1 times negative y over x squared is negative y over x squared divided by this. But this squared is just y squared over x squared. Y squared over x squared plus the 1. This can be rewritten. Get a common denominator here. So this would be change 1 to an x squared over x squared. So that way you can add these together. And so this part's the same as up here. Y squared over x squared is the same, but change 1 to x squared over x squared so that we have a common denominator. So now you can put these together with a single fraction bar and a single denominator and combine the numerators. You get x squared plus y squared over the x squared. And up here you still have this fraction, negative y over x squared. Well, now we have a fraction divided by a fraction. So to clean this up, you can write this fraction still, change it from division to multiplication. But when we multiply by the reciprocal of this, which is x squared over x squared plus y squared. Just reciprocate this. Pause, look at it. Can we do anything with this? Well, these x squareds divide out to 1. So you could say 1 over 1 if you like. And negative y times 1 will be negative y, and 1 times this will just be the same, x squared plus y squared. And there's a fairly reasonably cleaned up partial derivative expression for f. And now they want us to find the slope on the surface. And that surface point came from plugging this xy coordinate value in the xy coordinate plane to get the mapping value. But we don't need the mapping value to find the slope in the x direction on the surface. All you need is the Now we do need both variables, the x and the y. So now the partial derivative of f with respect to x at the point x equals 8, y equals negative 8 is, so right up here that's a y, put the negative 8 there, so negative 8 is positive 8 of course. Put the 8 right here for x and the negative 8 there for y, and we get 8 squared plus negative 8 squared. Clean this up now. Positive 8, as we said. 8 squared is 64. Negative 8 squared is also positive 64. 64 and 64 is 128. And now reduce 8 over 128 reduces to 1 over 16. So here's our slope on the surface in the x direction at x value 8, y equal negative 8. The z value, if we wanted to write it down, was what we said up here. When you put this in here, you get negative 8 over 8, which is negative 1. And arctangent negative 1 is negative pi fourths. But we don't have to write right here if we don't want to. They didn't ask us to write it. So it's okay. So 1 over 16. So here is our partial derivative formula with respect to x. Negative y over x squared plus y squared. Negative y over x squared plus y squared is the partial derivative of f with respect to x. And then we plugged in the point and we got 1 over 16. And that's this one right here. 1 over 16. Now we do it again, but with respect to y. In the y direction, the partial derivative will give us the slope value, slope function, the slope formula for the derivative of the function f at a point in the y direction. And as you can see, we get the same number this time, as I mentioned in the last problem. Sometimes you can get the same slope value when you're coming in the x direction or the y direction. And this happens this time. But notice the formula, the derivative formula is different. It's just that at this one point, you do get the same slope value. Because of, well, that's what's going on in this curve, on this surface. So now we differentiate this with respect to y. So right here, the derivative of f partially with respect to y of the two variable function x comma y is, what's the derivative of arctangent again of an inner function? It's 1 over, just like it was up here, 1 over 1 plus the inner function squared. So this part right here is the same as this part right here, times the derivative of the inner expression, the y over x. But now we differentiate y over x not with respect to x like we did up here, but with respect to y. So the derivative of y over x with respect to y, so that's x is being frozen constant. Pretend that was like a 7 on the bottom. So it would be a 1/7 times y, and the derivative of y with respect to y is 1, and it would be 1 times 1/7, which would be 1/7. Or if x was 10, then it would be 1/10 times the derivative of y, which is 1. You just get 1/10. So in general, when you freeze x and you differentiate this with respect to y partially, the derivative of y with respect to y is 1 times 1 over x, which is just 1 over x. So there's that. So the derivative of f with respect partially to y is 1 over 1 plus y over x quantity squared times the derivative of this inside with respect to y, which is just 1 over x. Clean this up. 1 times 1 over x is 1 over x. Do the same thing we did right here that we did up here in the denominator. Got the common denominator and we wrote it like this. So I did that right here, just didn't write all those steps down because it's the same thing. And so now we have 1 over x times x squared plus y squared over x squared. bring this up and change it from division to multiplication, and we get the 1 over x still times, reciprocate this, you get x squared over the quantity x squared plus y squared. Look to see if anything divides out. The x squared divided by x doesn't divide out to 1, but it divides out to x in the numerator. There's an extra multiplied x up here than down here. So we get 1 times x will be x. This is gone. Becomes a 1. And 1 times this denominator will still be the denominator x squared plus y squared with only an x in the numerator. So that's the partial derivative with respect to y. Hope that makes sense. Now plug in the point again, x equals 8 and y equals negative 8. Plug it into right here. So instead of x, you put the 8 right there, also right there. So 8 squared. And if there's a y anywhere, you plug in a negative 8. There's not a y there, there's not a y there, but there is the y there. So you put negative 8 squared plus the x squared value. Compute 8 in the numerator. 8 squared is 64. Negative 8 squared is also 64. 64 plus 64 is 128. Reduce it, and you get there's that same answer again. 1 over 16. And so here is our partial derivative formula with respect to y. X over x squared plus y squared. That's correct. And the partial derivative of y at the same point is 1 over 16 again. And so that's what this is. So we're correct. So I hope that makes sense, everyone. So problem 1, class. Explain whether or not the quotient rule should be used to find the following partial derivative. You don't have to differentiate it, it says. But if we did differentiate this partially with respect to y, well, let's see. There is a fraction bar here. It is a quotient. But what happens when you differentiate with respect to y? Then the other variable x is considered a constant, fixed. So in the denominator there is the variable x, but that's to be a specific fixed x value, any specific fixed. So you could say when it's 10, or if it's 4, or if it's 3, any of them. But once you start to differentiate, then you freeze it and hold it fixed. And so that's the derivative of x squared would be just like the derivative of 92, which would be 0. Well, if this was all by itself, but it's not. It's like saying something like this. If we had the derivative of y, if we had y over whatever, 20, and we say differentiate with respect to y of this you think of as 1 over 20 times y. It's a little easier to see this way. And so what's the derivative? It's the same thing as up here, but maybe a little easier to see. The multiplied constant 1 over 20 is fixed, and then because it's times, it stays there. If it was plus y, then the derivative of this would be by itself, would be 0. But because it's being, this fixed constant 1 over 20 is being multiplied by y, so the 1 over 20 waits and sits for the derivative of this part, and the derivative of y with respect to y is 1, so you would get 1 over 20 as an example. So this, by the way, if you had this like this, 1 plus 20, well, that would be, you could add them together, you get 21, and this is still fixed, and you would still have this like this. So when you have x squared plus 92, it's a little tricky because of the variable x squared. But when you differentiate partially with respect to y, then this is just like a number like a 1 plus 20 or a number plus 92. And so that stays the same. So when you differentiate, because there's a variable y up here, you're going to have, just like the 1 over 20 or 1 over 21, you're going to have this part sitting there waiting. And now what's the derivative of the numerator? And the derivative of x with respect to y, x is just considered a constant again, so that's all by itself because there's a subtraction right here. So the derivative of that would be 0, just like if it was a 2 or something. And then the derivative of negative y, or the derivative of y with respect to y is 1 with the negative in front of it, so you get negative 1. And so that would be the derivative, even though they didn't ask us to find it. But we don't need to use the quotient rule, because only if you're differentiating with respect to y, only if there was that variable y down here, well, then you would use the quotient rule. So I hope that makes sense. So no, you don't have to use the quotient rule because y only occurs in the numerator. So next class, I'd like to help you with number 8. Here is the function f. It's a two-variable function of x and y. Find the partial derivative with respect to x and the partial derivative with respect to y. They don't ask us to plug in a point this time to get the slope in the x direction or the y direction on the surface. They could have. So let's do this. So number 8. Given f of xy equals the square root of x plus y, just like it was on WebAssign, which you can rewrite as x plus y to the 1/2 power, of course, which will help us when we have to differentiate it. So the derivative of this function f with respect to, partially with respect to x, will be, well, you bring down the power to the front and it's multiplied power 1/2 times the same inner expression to the 1 less power than it was. We'll decrease 1/2 by 1 unit. 1/2 minus 1 unit is negative 1/2. And there it is. Times the derivative of the inner function, which is x plus y. Now what's the derivative of x plus y with respect to x? Well, the derivative of x with respect to x is 1. That's right here. Plus the derivative of y with respect to x partially, well, that y is considered a constant then, and the derivative of a constant by itself is 0. So this derivative of the inside becomes 1 plus 0. Clean this up. 1 plus 0 is 1 times 1 times this times 1/2. 1/2 times 1 is 1/2. This has a negative exponent, so you can move this base expression underneath, and it becomes times, next to the 2 in the denominator from the 1/2, times x plus y to the positive 1/2. And there is our partial derivative with respect to x. And again, they don't ask us to substitute a point in, a domain point, coordinate point. Now the derivative, partial derivative of f with respect to y, same idea. You differentiate this to it's a power, so you bring down the power again, so it's 1/2 times x plus y, again, the same interior function to the 1 less power, negative 1/2, just like it was up here, times the derivative of the inside expression. But now you differentiate the inside with respect to y. So what's the derivative of x with respect to y? Well, x is considered a constant, so the derivative of a constant by itself is 0, right there, plus, and the derivative of y with respect to y is just 1. There's the plus 1. Clean this up. 0 plus 1 is 1 again, 1 times 1/2 is 1/2. Move this base expression because the exponent's negative, and it moves underneath, and it becomes x plus y to the positive 1/2. And this turns out to be the partial derivative of this function f. It's the same partial derivative expression with respect to x and with respect to y. So there we go. 1 over 2, instead of x plus y to the 1/2, I just changed it back to a square root. This x plus y to the 1/2 can be a square root in the denominator. And we're good. So that was number 8. Next, I would like to help you with number 6. Z equal to cosine of 10x times y inside. This could be written as f of xy like you've been seeing, like down here in like number 8. But they just decided to write it in another way, which is fine. And they used the third dimension mapping range value or variable, which is a z. So notation wise, instead of saying this, for the partial derivative of f with respect to x, partial derivative of f with respect to y, you can write it this way. Instead of saying f, you can say z. The partial derivative of z with respect to x, the partial derivative of z with respect to y. So it's the same thing we've been doing, they just wrote it differently right here. How do we differentiate cosine of an inner expression? The derivative cosine of an inner expression is always, negative 1. Oh, I think I have it written down here. Number 6. The partial derivative of z with respect to x is, the derivative cosine is negative 1 times the sine of the same inner expression, 10xy, the same part inside, times the derivative of the inside expression with respect to x. What's the derivative of 10x times y with respect partially to x? So the y is considered a constant. It's a multiplied constant just like the 10 is. And so, I'm sorry, I'm getting very tired. I've been doing your videos all night long and in the other class all day yesterday, so I'm kind of hurting here, but we're getting close to being done. So the derivative of cosine again is negative 1 times sine of the same inner function times the derivative of the inner function with respect to x. And so y is treated as a multiplied constant just like 10, so the 10 times y sits and waits, and the derivative of the x with respect to x is 1, so it's 10 times 1 times y, which is just 10y. Put this multiplied 10y in front and multiply by the negative 1 if you like, and that's a way to clean it up. And we get the partial derivative of z with respect to x is negative 10y times sine of 10xy. Differentiate this partially with respect to y. Well, again, the partial derivative of z with respect to y is equal to, the derivative of cosine again is still the negative 1 times sine of the same inside expression times the derivative of the inside expression, but this time with respect to y. And so the 10 times x is fixed. It just waits as a multiplied constant in front, and the derivative of y with respect to y is 1, and so 1 times 10x will be 10x, and then I move the 10x in the front right away instead of writing an extra line. And so we get negative 1 times the 10x, and that's negative 10x times sine of 10xy. So I hope those two partial derivatives are understandable for you. And I just put them in the box here, of course. With respect to x, negative 10y sign, and with respect to y, negative 10x. And we're good. So I hope that's okay, everyone. These should be relatively easy. They're the same idea. So we already talked about 1, 2, 3, and 4, and 5 should be amongst the easier problems. When you do number A5, though, I'm leaving this one for you, but you're going to have to use quotient rule. But there's another problem in the assignment I'm going to help you with that has the quotient rule also. So it's very similar. So that's why I'm leaving you with number 5. We did 6, we did 7s for you. That'll be a simple, relatively simple partial derivatives to compute. Number 9 is like number 10 and number 11. Take the partial derivatives with respect to x and y, and then when you write them in there, and when you're done, then plug in the point ln of 9 for x and y equals 2, plug it into your partial derivative with respect to x, and clean it up, and then write down what it is. Just remember, if you have e to the, this is the x value, e to the ln of 9, e to the ln of 9, when ln of 9 goes into base e, they're inverses of each other, so e to the ln of 9 will compose out to just 9. So as long as you remember that, then it should be fairly nice. We did 10, we did 11. So next class, I'd like to help you with number 13. And strike that. Let's do 14 first, and then we'll do 13. So 14. Now we have a function f again, but it's not a function of 2 variables, x and y. It's a function of 3 variables, x, y, and z, which means the range value, or the function value, we can call it f, or we would call it a 4th variable that's not here, and then it could be any 4th variable you want, letter you want to use that's not already being used, but the common one is w, to use w equals. So this could be changed to w equals all of this. And so now this is a function of 3 variables, which we're not going to be able to graph, but we can still find the partial derivatives with respect to x, another partial derivative with respect to y, and another partial derivative with respect to z. And whatever those derivative formulas are, those partial derivative formulas are, then we can plug in the point they give us to, which now gives us the slope at this point on the 3 variable equation function, which is not, I don't think it's possible to visualize. But so we just go through the mechanics of it and take the derivative of these 3 terms with respect to x, with respect to y, with respect to z, and whatever we get, then you plug in negative 3 for x, 1 for y, and 3 for z, and to get the slope value. Okay, so let me show you that on my paper. Oh, so I said 14. So here is this function, 3 terms, 1, 2, 3. The partial derivative with respect to x of this 3 variable function, a function of x, y, and z. The derivative of this with respect to x, well, the other 2 letters are considered constant then. Y and z would be considered constants. So this letter y here, y cubed, is considered a constant, like if it was a number. Pretend this was like a 5. 5 cubed would be 125. 125 times x squared, the 125 would just sit there, or you can move it in the front, and then differentiate x squared. And the derivative of x squared would be 2, bring down the 2, 2x to the first power, times whatever this is, but we have to leave it as y cubed. We can't just change it to 125 or to 5 cubed. So the derivative of this term with respect to x is, bring down the 2, 2x to the first power times y cubed. So where did I write that? Right here. 2x y cubed. What about the derivative of this term with respect to x? Well, if this was just a 2x only, then the derivative of this would be just 2 times 1, because the derivative of x with respect to x is 1, times the constant that's waiting, multiplied constant, which would be times 2. So the 1 times 2 would be 2. But we also have this frozen constant and this frozen constant. So the derivative of this term with respect to x is the 2 times 1 times y times z, which is just 2yz. Right there. What about the third term? The derivative with respect to x, well, there is no variable x here. And we treat the other two letters, y and z, as constants. So this is all one constant. So the derivative of this, so pretend this was, just pretend this was a 2 and this was a 5. And you'd have 2 times 5 is 10 times 10 times negative 4 would be negative 40. And what's the derivative of negative 40 by itself? The derivative constant by itself is 0. So then, that's this minus 0 right here. So here is our partial derivative formula with respect to x, and you don't need this term. I crossed it out. Well, now they want us to plug in, and notice our partial derivative formula with respect to x has an x in it, a y in it, a y again, and a z in it. So the partial derivative with respect to x at the point negative 3, 1, 3, you just substitute. Wherever there's an x, you put a negative 3. Wherever there's a y, you put a 1. And wherever there's a z, you put a 3. And then just compute. So we're going to have 2 times x, but x is negative 3, times y is 1 cubed, plus 2 times y, but y is 1, times z, but z is 3. Compute this out. 1 cubed is 1, times negative 3 is negative 3, times 2 is negative 6, right there. Right here, 2 times 1 times 3 is plus 6. This term was 0, so we don't have to write it down. And negative 6 plus 6 is 0. So the slope does exist, and it just happens to be 0. And that's this one. So let's check this one. Two xy cubed plus 2yz. 2xy cubed plus 2yz. Oh. And so this one's correct, and we plugged it in into the partial derivative with respect to x, and we got 0, so that's correct. Now let's do the partial derivative of this up again here with respect to y, and when we get that done, we're going to plug in the point again. So the derivative of this with respect to y, so x squared is frozen as a constant, but it's multiplied so it stays. And the derivative of y cubed would be, bring down the 3, it would be 3 times x squared times y to the 1 less, y squared. 3 times x squared, y squared. What's the derivative of this term with respect to y? Well, it's 2 times x times z. Those are considered constants. They're frozen. So it's 2xz times the derivative of y with respect to y, which is a 1. So 2 times x times 1 times z is 2xz. Right here. And the derivative of negative 4yz with respect to y, well, the derivative of y again is 1 times negative 4 times z is negative 4z. And now plug in the point, negative 3, 1, 3. And so wherever there's an x, you put a negative 3. Wherever there's a y, you put a 1. And wherever there's a z, you put a 3. So if we do that, you get 3 times x is negative 3 squared times y is 1 squared plus 2 times x, 2 times negative 3 times z, which is 3. There's that term, minus 4 times z, 4 times z. Now just compute. Negative 3 squared is 9. Positive 9 times 3 is 27. Times 1 is 27. 2 times negative 3, negative 6 times 3 is negative 18. Negative 4 times 3 is negative 12. Now compute. 27 minus 18 is 9, and 9 minus 12 is negative 3. There's our f. The partial derivative of y of f at this point is negative 3. Here's this equation we got. 3x squared y squared. 3x squared y squared plus 2xz 2xz minus 4z plus 2xz minus 4z, and we're correct. The partial derivative with respect to z differentiate all three terms with respect to z, which means x and y are considered constants. So the derivative of this, this is just a constant, because x is a constant, y is a constant. So pretend x was 2, for example, and y was 3. 2 squared would be 4, 3 cubed would be 27, 4 times 27, that's 108, I think. And sorry, I'm losing my concentration. Sorry, where was it? Oh, so the derivative of this is, so this would just be constant, and the derivative of constant by itself is 0. So this is gone. The derivative of 2xyz with respect to z, the derivative of z with respect to z is 1 times, this is constant, this is constant, this is constant, so this all stays there. 2xy times 1, which is just plus 2xy. And that's this right here. And the derivative of the first term was 0, so I didn't write it down. The derivative of this term with respect to z, the derivative of z with respect to z is 1 times this constant, negative 4y. Now plug in the point again, negative 3, 1, 3. So put a negative 3 for x, and a 1 for y, and a 1 for y. 2 times negative 3 times 1 minus 4 times 1. 2 times negative 3 times 1 is negative 6. 4 times 1 is minus 4. Negative 6 minus 4 is negative 10, and there you go. So we got 2x minus 4y, 2x minus 4y, and then negative 10. And so they're all correct. So I hope that makes sense, everyone. So class, next I would like to do number 16. 15 and 16 are the same idea. Let's do 16 and you can do 15. Excuse me. So kind of sounds like a optimization problem or an extrema problem. When will the partial derivatives equal 0? Remember, like in single variable calculus, when you get critical points when the first derivative is equal to 0 or where they're undefined. And here we're finding where the partial derivative of x, the partial derivative of f with respect to x equals 0, and where the partial derivative of f with respect to y equals 0. So we're going to have to find, is there a point on this surface whose slope in the direction of the x value, the x direction, and the slope at that same point in the y direction, and both of those slopes are 0. So that's what they're asking us. So we need to take the derivative, the partial derivative of this with respect to x, and then again with respect to y, and then we're going to set them equal to 0. So here we go. So 16, f of xy is equal to this. You can always move this up, so it'll be 81 times x to the negative 1, or this one, 9 times y to the negative 1 if we need it. So what about the partial derivative of f with respect to x? Well, this term has only a y in it. 9 divided by y would be considered, y is a constant, fixed constant. So 9, it's like saying 9 divided by, pick a number, 2. The derivative of 9/2 would be 0. So the derivative of this is 0. The derivative of this with respect to x, well, the derivative of x with respect to x is 1, and then this is, again, considered a constant, so it would be 1y, or just y. So that's this part. This is 0. It's not showing. Bring this up, you get 81x to the negative 1 power. 81x to the negative 1 power. So if we have 81 times x to the negative 1 power, move this up so you don't have to use the quotient rule. Now you can use the power rule. Bring down the negative 1 and you get negative 1 times 81 times x to the 1 less, which is negative 2. This cleans up as negative 81 over x squared. And so that's what's right here. So the derivative of 81 over x is negative 81 over x squared. The derivative of this term is 0, and the derivative of this is 1y, or just plus y. And then they ask us, when will this partial derivative with respect to x equal 0? So you set this partial derivative expression, negative 81 over x squared plus y equal to 0. You can solve for x or for y. I solve for y because it's easier. Move this term over and it becomes positive. So when will f of the partial derivative of f with respect to x equal 0? When y equals 81 over x squared. Well, that doesn't help us a lot yet. So now we also look when the partial derivative of y, the partial derivative of f with respect to y is equal to 0 as well. But first we have to differentiate this with respect to y. So when you differentiate with respect to y, then the other variable is considered constant. So this is like an 81 over, pick a number, say 2. Well, then the derivative constant by itself is 0. So that's 0. The derivative of this, you'd move the y up, it would be y to the negative 1. 9 times y to the negative 1. It's just like this one, except it would be a 9. Y to the negative 1. Bring down the negative 1 and you get negative 1 times 9 times y to the 1 less, negative 2. move it underneath, and you get negative 9 over y squared. And then the derivative of x times y with respect to y, the derivative of y with respect to y is 1 times the constant, frozen constant x, which would just be 1 times x, which is x. When does this equal 0? When does the partial derivative of f, partial derivative of f with respect to y equal 0? When this derivative is equal to 0. Solve for x is easier here. That's when x equals 9 over y squared. So what we want to do now is, this is when the partial derivative of y, the partial derivative of f with respect to y equals 0. And this is when the partial derivative of x, the partial derivative of f with respect to x equals 0. And now you can combine these two. So you can find out at what points what xy coordinate plane domain points, well, their mapping will be a point on a surface. And when does the partial derivative with respect to the x direction equal 0, and when does the partial derivative of y equal 0? So we know that happens for the first one right here at this relationship, and the second one at this relationship. So combining the two, these two, I took this one right here, x equals 9 over y squared, and put it into this one. You could also have put this one right here, right down here. Either way, you will get the same values. So if you do plug 9 over y squared right here for x, you get y equals still 81 in the numerator still. Instead of x squared, you get 9 over y squared. Now you've eliminated the x variable, so now we can solve this for y, and we'll know at least the y values. So 81 over 9 over y squared. I put an 81 over 1. 9 squared is 81. Y squared is y to the 4th. So we get 81 over 1 divided by 81 over y to the 4th. Well, you have a fraction divided by a fraction. So you can clean this up right here, and you get this y still equals 81 over 1 times the reciprocal of this, which is y to the 4th over 81. The 81s divide out to 1. So you get 1 times y to the 4th is y to the 4th. 1 times 1 is just 1 on the bottom. You don't need to write it. So we get y equals y to the 4th. Now, I move this y over to the other side because we're trying to get the y values, where both of these partial derivatives equal 0. Once we know the y values, we can plug it right in here, and that'll give us the x value of that coordinate, xy coordinate point. And so now, if you move the y over, it becomes subtract y. We get y to the 4th minus y equal to 0. Now this is 0. Factor out a y here. We get 0 equals y times what's left, y cubed minus 1. Set this multiplied factor equal to 0, and you get y equals 0. Set this factor, y cubed minus 1 equal to 0. Solve for that. This one's done. Move over the negative 1, you get y cubed equals 1. Take the cube root of both sides, you get y equals 1. So according thus far, we get both partial derivatives will equal 0 when y equals 0 and when y equals 1, unless there's an issue with any of them, like a domain issue. And look back up here at the original function, 81 over x plus 9 over y plus x times y. At y equals 0, right there you get 9 over 0, and that's a division of 0. That's unfortunate, because that means there's no mapping for this f, this surface function f of xy at y equals 0, regardless of what x is. At y equals 0, you're going to have 9 over 0, which is an undefined number, which means there's no mapping. And if there's no mapping, then the derivative in the x or y direction cannot be 0, because there's no point there. And if there's no point there, then there can't be a slope value there. So that means we have to eliminate y equals 1 from the possibilities of where the partial derivatives are equal to 0. So what's the only y value left? Y equals 1. If you do plug a 1 up here, that's not a division. That's a division of 1. That's not a problem. So let's find what I'm sorry, I think I said that wrong. When y equals 1, you would put 9 divided by 1, which would be 9. That's okay. And this, we don't know about x yet. So we're going to continue with y equals 1. I wrote over here, at y equals 0, f of xy is undefined, which I told you about because you get 9 divided by 0. Thus, f of x, the partial derivative of f with respect to x and the partial derivative of f with respect to y can only equal 0 at y equals 1, not y equals 0, because the function is not defined at y equals 0, and therefore it can't have a mapping. And as I already said, if it doesn't have a mapping, then there can't be a slope there. And so there can't be a slope of 0 there either. So that's out. So what's left? Thus f of the partial derivative of f with respect to x can equal the partial derivative of f with respect to y can equal 0 only at y equals 1. Unless we find out there's an issue with that as well. Well, if you put a 1 there, that's okay. 9 divided by 1. If you put a 1 there, that's okay. You're not going to get a division of 0. So let's get the x value then. So when y equals 1, you can plug it into whichever one of these two you want that came from this and this. So this one's maybe a little easier. If you put 1 right there, you get 9 divided by 1 squared. So 9 divided by 1 squared is 9, so you get x equals 9. And so there we go. So the only xy coordinate point whose mapping is on the surface will have a partial derivative with respect to x and a partial derivative with respect to y at both equal to 0 at that one point. That one point is when x is 9 and y is 1. They could ask for the z value as well, or the mapping value, and you would just plug a 9 right here and a 1 right here and a 9 right here and a 1 right here and compute. And we will get a mapping value. And by the way, if we plug this 0.9, 1 into both partial derivatives, let's see what happens. Right here you'd put a 9 right there and a 1 right there. 9 squared is 81. Negative 81 divided by 81 is negative 1. Plus y, which is 1. Negative 1 plus 1 is 0. And you do get a partial derivative of 0 at this point, 9, 1. We also better get a partial derivative slope value of 0 also at 9 comma 1 on for the partial derivative of f with respect to y. Let's check it. If you put a 1 in for y and a 9 in for x, you better get 0 for the slope value. Negative 9 over 1 squared is negative 9 over 1, which is negative 9, plus x, which is 9, and negative 9 plus 9 is 0. So it does work. So where does this function f have partial derivatives that are both equal to 0 at the same point? And that is at when x is 9 and y is 1. If they would have said at what x, y, z, then you would have just put 9 for x, y, 1 for y, and then plug the 9 right here, the 1 right here, the 9 right here, the 1 right here, compute, and then you would know the z value, the range value. And so you're going to do this, so we're correct. And you're going to do the same thing for 15. I want to help you with one more. And 17 and 18 are very much the same. Can't remember now if we did 13 or not. So I think I skipped 13, so I want to come back and do that one, and then we'll do number 18, and then that'll be it. So number 13, everyone, find the first partial derivatives with respect to x, y, and z, because this is a function with respect to 3 variables, just like 14 was. And then we're going to find the 3 partial derivative formulas with respect to x, with respect to y, with respect to z. But then they don't ask us to plug in any point or anything. But the reason I want to help you with this one is because, well, let me just go to my paper. So here's 13. Given w equals 9xz over x plus y. So one of them is the partial derivative of w with respect to x. And now look at this function. It's a quotient, and there's an x in the numerator and in the denominator. So when we differentiate a function that has, the rest are considered constants because you freeze them, hold them constant. And so when you differentiate a rational function that with respect to a variable, and there's a variable in the numerator and the denominator, then you use the quotient rule. So the quotient rule is the denominator squared, and in the numerator you put these 4 grouping symbols with the 2 of them together with multiplication, the right 2 together with multiplication, and a subtraction sign in between. And then in the first grouping, well, the first grouping symbol, you say the original denominator, which is an x plus y, no change there, times the derivative of the numerator with respect to x. And now 9 is a constant, z is a constant, so the 9 times z is weighting, and then times whatever the derivative of x is with respect to x, which is just 1. So 1 times 9 times z is 9z. Subtraction always. And then in the third grouping symbol, you put the derivative of the original denominator with respect to x. What's the derivative of x with respect to x? 1. Plus, this is separate, what's the derivative of y is considered a constant here. It's fixed, it's frozen. And the derivative of constant by itself is 0, so you'd get, right here you get 1 plus 0, which you don't have to write the plus 0. So I just wrote 1. Times the original numerator, which is the 9xz. So there is the quotient rule. Now clean it up. Well, the denominator squared stays, unless you want to multiply it out. Not really a need to. If we multiply this out, distribute 9z times x, you get 9xz in alphabetical order. 9z times positive y would be positive 9yz in alphabetical order. Minus 1 times 9xz would be negative 9xz. 3 terms in the numerator. 9xz plus 9yz minus 9xz. These two subtract out to 0. So that's friendly. So what's left in the numerator? Just the 9yz right here over the x plus y squared. So I hope that makes sense, everyone. That's the partial derivative of w with respect to x. 9yz. Partial w with respect to x. 9yz over x plus y squared. 9yz over x plus y squared. And that's correct. Do it again now. The partial derivative of w with respect to y. So the partial derivative of this with respect to y. So the partial derivative of w with respect to y is, well, you have a y in the denominator. You don't have to use quotient rule this time. You could put a parenthesis around this to the first and move it up and it become to the negative one. But I think it's just as probably easy, just enough to leave it as quotient rule here. So we get the denominator squared again, like we did over here. And now in the numerator you have the 4 grouping symbols we have to fill in with the subtraction sign in between. So it's the original denominator, x plus y, times the derivative of the numerator with respect to y, but there is no y in the numerator. So these are constants. 9 times a constant times z, a constant, is some new constant, some number. And the derivative number by itself is 0. So that's why you see the 0 here. Subtraction always times the derivative of the denominator, original denominator, with respect to y. So the derivative of x by itself would be 0, and the derivative of y with respect to y would be 1, so you'd get 0 plus 1, which is just 1, right there, times the original top, which is the 9xz. So that's the derivative of w with respect to y. Clean this up. X plus y squared still in the denominator. In the numerator, 0 times x plus y is 0. That all goes to 0. It's gone. Negative 1 times 9xz is just negative 9xz. And so there's our partial derivative of this function with respect to y. Negative 9xz. Negative 9xz over x plus y squared. And there's the friendly green check mark. And the last one, the partial derivative of w again, but with respect to z. With respect to z. The z is not in the denominator. So this is like if you would have had 9xz, just pretend, over 4. Over 4, just pretend. Because this is considered a constant plus a constant, which is a brand new constant. And so if you had like a 9 over 4, then that would just wait. The 9 over the 4 would wait. And then you would differentiate, and the x would wait. And you differentiate z with respect to z, and that's 1. So you get 1 times x times 9, which is 9x, over x plus y. So I hope that makes sense. (9x) over x plus y. 9x over x plus y. And there's our nice green check mark. Last one, everyone. (17) and 18 are very similar. I picked the slightly more complicated one, number 18. So we have this function right here, z equals this. Notice this over here is with respect to x and y. So this is a two-variable, z is a two-variable function, where z is the range variable or range mapping value. And now they want us to take the partial derivatives. So let me show you that. So 18 so given z equals 9 times x times e to the y minus 6 times y times e to the negative x. First, let's find the first partial derivatives with respect to x and y. So the partial derivative of z with respect to x, so let's differentiate these two terms with respect to x. So y is fixed, constant, so e to the y is a fixed constant, just like the multiplied 9 is. And the derivative of x with respect to x is 1. So we get 9 times 1 times e to the y, which is 9 e to the y. So that's the derivative of this term. What about the derivative of the second term with respect to x? The multiplied 6 and the multiplied y is fixed, so it sits there. And then so it's minus 6y, fixed, times the derivative of e to the negative x. Well, the derivative of e to the negative x is repeated, e to the negative x, times the derivative of the exponent. And the derivative of negative x with respect to x is negative 1. So that's this. This can clean up a little bit. 9 e to the y is 9 e to the y. This negative 6 times this negative 1 is plus 6 y e to the negative x. Oh, you can switch this around if you want. So there's our partial derivative with respect to x. Now what about the partial derivative of this function z with respect to y, the other partial derivative, first partial derivative? So differentiate this term with respect to y. Well, the derivative of e to the y is just e to the y. And the multiplied 9 and the multiplied x are constants, so they sit there, and you get 9x times e to the y for the derivative of the first term with respect to y. And the derivative of the second term, well, the negative 6 times y times e to the negative x. The 6 is a multiplied constant, the e to the negative x is a multiplied constant, and the derivative of y with respect to y is 1. So we get negative 6 times 1 times e to the negative x, which is negative 6 times e to the negative x. So there's our first partial derivatives, one with respect to x and the other with respect to y. So I hope that makes sense, everyone. Now, so nothing new so far with number 18. Well, this part is new, not terribly difficult or anything, but just like we have higher order derivatives with single variable functions like f prime of x and then f double prime of x is the second derivative and f triple prime or the third derivative and so forth, we can have higher order partial derivatives as well. These are the first partial derivatives with respect to x and with respect to y, of z, by the way. So what would be the next order of partial derivatives would be the second partial derivative. The second partial derivative. But to compute the second partial derivative, you first have to have a first partial derivative, which we have both. The partial derivative of z with respect to x is this over here. The partial derivative of z with respect to y is right here. And so now we're going to take this one and differentiate again partially, but not with respect to what we already did, but with respect to the other variable, which is the y. And then this is called a second order or a second partial derivative, but it's a mixed partial derivative because we already differentiated it with respect to x. Now we're going to take this answer and differentiate it with respect to y. So we took right here, we took the partial derivative of z with respect to x. That was this right here. This. And now we're going to, which is right here still. And now we're going to take this and differentiate it with respect to y. So let's do that. And then we'll talk about the notation here as well. So what's the derivative of these two terms with respect to y? Well, that means x is held constant. And so what about the derivative of this term? Well, the derivative of e to the y with respect to y is just still e to the y times the 9 that's waiting. So it's just 9e to the y. It just repeats. And the derivative of 6 times y times e to the negative x with respect to y, well, the derivative of y with respect to y is 1. The multiplied 6 weights and the multiplied e to the negative x weights like constants, as constants. So there will be 6 times 1 times e to the negative x, which is just 6 times e to the negative x. And so here is our second partial derivative, but the first derivative, the first partial derivative was the partial derivative of z with respect to x. That's this part, which was this answer, which is right here. And then you differentiate this answer with respect to y. Notice we don't write a z right here because we're differentiating with respect to y whatever the answer was to this partial derivative, which was the partial derivative of z with respect to x, which was this right here, which is this. And then you differentiate it with respect to y, and that's a second partial derivative, but a mixed one. Because first we differentiated partially with respect to x, and then whatever we got, then you differentiate it partially with respect to y. Therefore, second partial derivative, but a mixed one. Mixed meaning both variables. And this is how you can write it like this. This is one way to write it, notationally speaking. Here's another way to write it. This is a way to write it, but only after you've done the first partial derivative and you have it finished, then you can write it like this. And this will be the second partial derivative with respect to y. Another way to write it is like this. And this is take the function f, but when it's written this way, you read it from left to right. I don't know why they played this game, but you start here and you say first you differentiate f with respect to x, which is what we did up here, which was this right here, and then you differentiate it with respect to y. So you read this one first and then this one. But if it's written this way, the second partial derivative of z with respect to partially with respect to y, partially with respect to x, when it's written this way, then you start from this one. And then you do this one. So this means first partially differentiate z with respect to x. Partially differentiate z with respect to x. That's what we did. And whatever you get, then differentiate it a second time, but with respect to y. So when it's written this way, you look here and you do this one first. This is first. and this one's second. When it's written this way, it's the opposite. You do this one first, and you do this one second. And we got 9e to the y plus 6. Oh, it's up here. 9e to the y plus 6e to the negative x. 9e to the y plus 6e to the negative x. So there's one mixed second partial derivative. Let's also now do another second partial derivative. This was the first partial derivative of z with respect to y. So we took this and differentiated with respect to y, and we got this. Now we're going to take this and differentiate it with respect to the other variable that we didn't do yet, which is a z. How do you write that? Several ways. Here's one way. Take the partial derivative of z with respect to y, which is what we did. Took the derivative of z partially with respect to y, and we got this answer. Now differentiate this answer partially with respect to x. And so take this answer, which is right here, and differentiate this partially with respect to x. So let's differentiate this with respect to x. What's the derivative of this term with respect to x? Well, the derivative of x with respect to x is 1, and 9 times 1 is 9. Y is fixed, so this stays. 9 times 1 times e to the y is 9e to the y. And the derivative of this with respect to x, well, negative 6 is waiting. The derivative of e to the negative x is e to the negative x times the derivative of the exponent, and the derivative of negative x is negative 1. So the derivative of e to the negative x is e to the negative x times the derivative of this, which is negative 1. But the negative 1 times the negative 6 that was waiting, it becomes a positive 6. So positive 6 e to the negative x. And notice, this second partial derivative, where we first differentiate with respect to y and then with respect to x, we get this. And when you did the second partial derivative that was mixed in the other order, you differentiate first with respect to x and then with respect to y. We did that, and we get the same thing as this one. And note, the second mixed partial derivatives are always equal. The second mixed partial derivatives are always equal. Not just for this two-variable function, but for all two-variable functions. That kind of makes sense. If you differentiate this partially first with respect to x, and then whatever you get, differentiate with respect to y, and then do it the other way around, you get the same answer no matter what. So that's the other second partial derivative that was mixed, which is this one. The second partial derivative of z that's mixed. When it's written this way, you start from over here. Differentiate with respect to y first, and then whatever that is, differentiate with respect to x. And we got 9, we got the same answer as this one. Green check. Well, that's 2 out of 4. What's left? This one right here and this one right here, which is still a second partial derivative, but it's not a mixed one. It's not a mixed one. Neither one. So we go back up to here and look at our first partial derivatives. This one was with respect to x, and this was the answer. And now we differentiate this again with respect to x. With respect to x. So it's a second partial derivative, but with respect to x the first time and with respect to x the second time. Both times. So you write it like this, notationally. The second partial derivative of z with respect to x both times. Both the first time partially and the second time partially with respect to x. And what is the derivative of this? This is already the first derivative of z with respect to x, partially. And now take this and differentiate that with respect to x, which gives us our second partial derivative. So what's the derivative of this term all by itself with respect to x? Well, there's no x here in this first term. And y is considered a constant, so e to the y is still some constant. Times 9 is a constant. 9 times e to the y, and a constant times a constant's a constant. And what's the derivative of any constant by itself? That's 0. So the derivative of this term is 0. What's the derivative of this term? The derivative of this term with respect to x, y is frozen, 6 is frozen as a constant, so the 6 times y is waiting. And then what's the derivative of e to the negative x with respect to x again? Well, it's e to the negative x times the derivative of the exponent, which is negative 1. That negative 1 times 6y, though, becomes negative 6y e to the negative x. And this was 0, remember, so it's just negative 6y e to the negative x, which is right here. Which is right here. And then lastly, the second partial derivative of z with respect to y twice. The second partial derivative of z with respect, The second partial derivative of z with respect to y twice. I went over 2 hours. Now I'm going to have to split this up. I kind of forgot about that. But we're done. We're almost done. But that's my issue. So take this partial derivative of z with respect to y, which was this. We differentiate this with respect to y partially, and we got this. Now differentiate this again, but with respect to y again. So what's going to be the derivative of this first term with respect to y? Well, the 9 times x are held as constants. So they're just waiting for us to differentiate e to the y. And the derivative of e to the y with respect to y is just e to the y again. So we get 9x e to the y. That's that part. And the second term, negative 6 times e to the negative x, it doesn't have any y here. So the negative 6 is a constant, e to the negative x is a constant. A constant times a constant is still a constant, but there's no y here. So the derivative of constant all by itself is 0. So that's why the derivative of this term goes to 0, and all it's left is the derivative, whatever the derivative of this was, which we said was this right here. And it's the same thing because, again, the derivative of this term right here with respect to y, the derivative of the y is still just e to the y. And then x is waiting, and the 9 is the multiplied x, the multiplied 9 is waiting. And that's why the derivative of this term is the same thing as it was. And so here's the last of the 4 second partial derivatives of z. 9x e to the y. 9x times e to the y. And we are correct. So everyone, I hope that helps you understand partial derivatives of 2 variable functions, or even with 3 variables. We had a couple here, a function with respect to x, y, and z, and take the partial derivatives of that, which are 3 of them then. These are first partial derivatives only. So, So you're left with number 17, which is the same as number 18. Find the 4 second partial derivatives. I think I picked a slightly harder one than this one. Will be a little bit easier. We did this one, 16. When is the partial derivative of f with respect to x equal to 0, and also the partial derivative of y with the partial derivative of f with respect to y equal to 0 simultaneously. So you're going to do the same strategy with this one. We did 14. We did 13. 12, you can do that one yourself, should be fairly nice. Differentiate this partially with respect to x only, with respect to y only, with respect to z only. That's a friendly function to differentiate. We did 11 already. We did 10 already. 9 is for you. Differentiate this partially with respect to x and with respect to y. Write down those formulas and then plug in the point ln of 9, comma 2. And remember, when x is ln of 9 and you put e to the ln of 9, they compose out to just 9. We did number 8 already. These up here now are getting easier. Find the first partial derivative of f with respect to x. Well, you can just look at it and do it. The derivative of x squared is 2x. The derivative of 9xy with respect to x, the derivative of x with respect to x is 1, so you're left with negative 9y. And the derivative of y squared by itself, when y is a constant, the derivative of a constant by itself is 0, so that's it. And now you guys, ladies, can do this one. The partial derivative of this same function, but with respect to y. We did this one already. This is the one that will be somewhat interesting, because when you differentiate with respect to x and with respect to y, you're going to have to use quotient rule on both of them. But it's similar then to the one down here we did with the quotient rule, which was number 13. So I'm leaving that one for you. This will be fairly simple as well. The derivative of e to the power is just e to the power times the derivative of the power. And when you take the partial derivative with respect to x, for example, or how about with respect to y, for example, you get the derivative of e to the xy repeats e to the xy times the derivative of the expression inside the exponential function, and the derivative of x times y with respect to y. Well, the derivative of y with respect to y is 1, and x is held constant, so 1 times x is just x, so times x. Or you can put the x in the front if you like. But either way is fine. And number 3 and number 2 should be fairly routine. Number 1 we already talked about. Okay, class, so phew, that was kind of long for me, at least, and probably for you too. So I hope this helps you all. Please listen earnestly, try to learn sincerely and earnestly, and that's what this is all about. So I hope these lecture videos are helping you and you're using them honestly and sincerely. Yeah. So I will try to make section 13.4's lecture video tomorrow, and then we just keep going, one section at a time. Okay, everyone, so I wish you all well. Thank you for your patience and listening and learning, and we'll see you next time. So this is Mr. King saying goodbye for now, and take care. Bye, class.